Hi, so this is lesson 2 of our new topic, which was energy resources and energy transfer. So if you remember, last lesson we looked at different types of energy. Okay, so we looked at heat, light, sound, kinetic. Remember, that's just another name for movement energy, if anything's moving. Electric energy, sometimes called electrostatic energy. And different types of potential energy, so chemical potential energy, so the energy stored in chemicals, fuels and food. Gravitational potential energy, the energy stored when we lift something up. Elastic potential energy, the energy stored when we stretch a spring or a piece of elastic. And nuclear energy, which we'll talk about more in year 11, the energy stored inside the nucleus of an atom. Okay, so for example, I've got here one of those egg timer sort of things. Somebody bought me this for Christmas. So I turn this round. Okay, it's actually got iron filings in this one. It's a magnetic one. Yeah, they've gained gravitational energy because they're higher. And they're falling. So that gravitational energy is turning into kinetic energy. So we've got an energy change there. Gravitational energy changing to kinetic energy. Can you see that? This one's actually got a magnet at the bottom. Okay. So here's a very simple example. Okay, so there's an energy change takes place inside of this is an old-fashioned, what we call a filament light bulb. And instead of change in physics, we hear transfer, energy being transferred. Okay, so this lamp, it takes electrical energy and it transfers it into heat and light energy. And remember last lesson we looked at drawing an energy flow diagram. Now I'm just going to introduce to a slightly more sophisticated version of this diagram called a Sankey diagram. So here's a Sankey diagram, and it's similar to the energy flow diagram, but the sizes of the arrows, the thickness of the arrows is proportional to the amount of energy. So as you can see here, this light, if we put 500 joules of energy into this light bulb, okay, only 75 joules is turned into light energy. 425, I don't see you can think you see all that because my picture's there, is turned into heat energy. So as you can see, so there's a thin arrow here showing only a small amount of energy is turned into light, whereas a much bigger amount is turned into heat energy. Okay, but notice, of course, according to the conservation of energy, the total amount of energy stays the same. Okay, 75 joules is turned into light energy, 425 joules is turned into heat energy, but if you add those two together, okay, of course that equals the amount of energy we put in. So we've not lost energy or gained energy, we've just changed energy. Okay, now notice of course that whilst the total amount stays the same, not all of it is what we call useful. This is a light bulb. We want it to produce light energy. We don't want it to produce heat energy. So in a way this is wasted energy. So we have a quantity in physics called the efficiency. And efficiency is just a measure of how much energy is turned into what we want it to be turned into. So this is a formula, another formula we've got to learn. Okay, so efficiency, if we measure it in percent, is the useful amount of energy out. And later on we'll talk about, we can also use the word power there instead, divided by the total amount of energy in, or the power. And if you multiply that fraction by 100, you'll get the efficiency in percentage. Okay, so when we finish this, I'd like you to go back and I'd like you to copy that, please, with a title, underlined with a ruler. Okay, and that's a formula that we need to learn. And in a few moments, we're going to try to use that formula. So let's have a look at some examples. Okay, so this is a fairly typical filament light bulb, sort of old-fashioned light bulb, like we just talked about. So as you can see, the useful energy out is 75 joules. The total energy in is 500 joules. Okay, so if we do 75 divided by 500 and multiply the answer by 100, we get 15%. So basically that means that only 15% of the energy we put in is converted into light. That's obviously not very good. Okay, if we look at an energy efficient light bulb, so these bulbs were developed 15 or so years ago, we can see here that for every 100 joules we put in, 75 joules is turned into light energy. So the useful energy out is 75, the energy put in, the total energy put in is 100. 75 divided by 100, if you put in your calculator, is 0.75. Multiply by that 100, you get 75%. And obviously that's much better. Okay, it'd be interesting if any of you know who that man is and why I've used his picture there. It's a little out of date. Okay, so attached to this lesson is a worksheet. It's called Lesson 2 Efficiency Worksheet. Okay, and it's using the formula I've just given you. So you need to go back now, you need to copy that formula into a book and then have a go at the worksheet. You will need a calculator. Obviously, please message me if you need any help with that. When you've answered the questions, put the answers on the Word document, okay, and upload it to Show My Homework. I'm going to stop there.